Welcome everyone to Chapter 2. In this chapter, we're going to be introducing one of the main topics in Calculus 1, that is the idea of the derivative. So in section 2.1, we're going to be introducing what is the derivative. We're going to look at how to take some basic derivatives, some general properties, and then we're going to continue throughout the chapter looking at more and more properties and problem solving with these derivatives. So at the end of the previous chapter, we introduced the idea of finding the slope of a tangent line and the concept of instantaneous rate of change. Well, that concept is the derivative. Okay, so the derivative is basically just giving a name to that idea. So notationally, we say that the derivative is written like this. So it looks like f of x with a little like apostrophe or a tick mark up here. This is read as f prime of x. So this is what we call prime notation. So the derivative f prime of x of the function f is the slope of the tangent line to f of x, also known as the instantaneous rate of change of x, of f with respect to x. So when we look at how to define the derivative, we use the same definition that we had for the instantaneous rate of change in the previous section, and that is by taking the limit of the difference quotient. So we take the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, and this is known as the limit definition of the derivative. Okay. Let's take a look at an example. So we have the function f of x equals x squared plus 6x minus 2. Find each of the following and interpret the result. So first it asks for f of 5. Okay, we can get f of 5 by just plugging in 5. So we get 5 squared plus 6 times 5 minus 2. That's 25 plus 30 minus 2. So that's 55 minus 2 is 53. That is f of 5. Now it asks us for f prime of x. So it wants the general formula for the derivative of this function. So we're going to find that by taking the limit as h approaches 0 of f of x plus h. So that means when we go through this function, instead of an x, we're going to have an x plus h here, and here, and here. Okay, so that's going to be x plus h squared plus 6 times x plus h minus 2. And then minus f of x, so that's just the original function itself, all over h. Be very careful and deliberate with your inclusion of parentheses here, because everything needs to get distributed properly in order for this to work. So with this first set, this is x plus h quantity squared. So it's not just like x squared plus h. This is x plus h times the quantity x plus h again. So that's going to give us x squared plus 2xh plus h squared. We need to distribute the 6 as well. So again, that's another easy step to overlook, but it distributes to both. Minus the 2, and then distribute this negative to each of the terms back here. So minus 6x and plus 2. all over h. Now, if this works as it should, we should have some cancellations that we can do that allow us to simplify. So notice here there is an x squared and a minus x squared. There is a 6x and a minus 6x. There is a negative 2 and a plus 2. So if we look at what's left, we have 2xh plus h squared plus 6h all over h. There is a common factor of h in the numerator. So we can go ahead and factor that out. So 2x plus, there's still an h left there, plus a 6 all over h. This h will cancel with that one. So all we have left is the limit of 2x plus h plus 6. And as h goes to 0, that middle term disappears. And we are left with 2x plus 6. Okay, and that is our formula for f prime of x. Okay, for that derivative function. So if we wanted to find, again, the slope of the tangent, the instantaneous rate of change, if we want to find the derivative of this function at any x value that we want, now all we need to do is just plug that x value into here, and we can get the slope. We can get the derivative. And speaking of plugging in any x value we want, part C is asking for f prime of 5. Now, if it had just asked us for f prime of 5 from the beginning, we could have just put in 5 into the formula. But having the general formula first is much more powerful because this general formula allows us to find the derivative for any x's that we need, not just one at a time. So we just do 2 times 5 plus 6, and that is 16. Just like that. Now, as we look to the top of the next page, we're going to talk a little bit about notation here. So if we have a function y equals f of x, then each of the following represent the derivative of f of x. So f prime of x we already know. Another common one is y prime. Okay, so instead of f prime, it's y prime. Then we have our first kind of alternative notation. This is dy over dx. Okay, so we just read it dy dx. Okay, this is called the Leibniz notation of a derivative, named after one of the creators of calculus. So this is dy dx. If we're using f instead of y, we can make it df dx. And the Leibniz notation can be particularly useful when you're applying the derivative to a function, because you can write it like this. So d dx of f of x, like that. This is telling us to take the derivative with respect to x of f. Okay. So all of these are equivalent, and we want to try to feel comfortable with using any and all of them because they all represent the same thing, and you might see one or another depending on like the context, depending on how we're using them. If we want to evaluate the derivative of it at a specific value of x equals a, then we use f prime of a. But if we are using the Leibniz notation, the dy dx notation, we would use what we call an evaluation bar right next to it, and then put the x equals a value down there, whatever that might be. So again, this is an evaluation bar. So just in case you encounter that notation anywhere, you'll know what that means. That just means we're plugging in that specific value. All right, now one of the, I guess, perks of working in a course that is kind of a shortened version of calculus is that we get to jump right into a lot of the derivative rules and properties that exist for us to use. So we're going to get a bunch of new rules now that we're going to be able to apply to functions when we take their derivatives. So first up, derivative of a constant. If you have a constant function y equals c, where c is any real number, if you picture what that looks like, a constant function is just a horizontal line, right? Y equals 5 or y equals 7 or whatever the case may be. If you try to find the slope at any point, that's still a horizontal line, right? That's completely flat. So they're going to have a slope of 0 everywhere. So the derivative of a constant is 0. Okay, so that's an important one. Here we have one of our most used properties because we work with polynomials so much, and that is the power rule. The power rule says if you have a function x to the n, okay, so x is a variable and n is a real number, to take the derivative of this, we're going to take that n value, bring it down to the front of the formula, and subtract 1. So we bring down n times x to the n minus 1 power. Okay, so this is the power rule. Power rule says if you're taking the derivative of the function x to the n, that you bring down the n to the front and then subtract 1 from the power. This property does extend to ones where maybe you can't even see the power. So like the derivative of x by itself, if y is x to the first, like this, then the derivative of that would be 1 times x to the 1 minus 1. So 1 times x to the 0, but x to the 0 is just 1, so we just get 1. Okay, so the derivative of x is 1. The derivative of a constant is 0. The derivative of a power function is given here, n times x to the n minus 1. Now, what if we have constants involved with the functions? So if f of x is differentiable and c is a constant, the derivative of c times f is equal to c times the derivative of f. So if you have a constant times a function, you can multiply the constant in first and then take the derivative, or you could take the derivative first and then multiply the constant after. It won't change the value in any way. So you can pull constants out of derivatives. You can also move them in. You can go backwards, move them back into the derivative. So a commonly used case of this, if you have c times x, the derivative of x is 1. So you just get c times 1, which is just c. So the derivative of cx is just c. So this property, what it allows us to do is basically like ignore constants as we go through the derivatives. So we can just say, so note constant multiples, and this is my own terminology that I like to use, just go along for the ride. So when you're taking the derivative, so like if you had again, like 5x, something like that. When you take the derivative of that, the 5 is just tagging along. It's just going along for the ride. So we take the derivative of the x is 1, and the 5 is still there, but then 5 times 1 is just 5. So it didn't change how we took the derivative of the x. It just gave us a little extra something attached to it. Okay. If we're taking the derivative of a sum or difference, then we have f and g both being differentiable functions. The derivative of f plus g or f minus g is equal to the derivative of f plus or minus the derivative of g. So again, addition and subtraction do not impact the derivative. You can take the derivative term by term. So note, with addition and subtraction, we take derivatives term by term. So you don't have to come up with some, convoluted, crazy formula to be able to take a derivative of like all the terms at once. Really, all we need to do is look at the first term and take the derivative. Then go to the second one, take the derivative. Go to the third one, take the derivative, etc., etc. So it makes it a lot simpler on us. Let's take a look at some examples. Got a bunch of functions here. So, first step, we have the function f of x equals 4. 4 is a constant function, and the derivative of a constant, always 0. Okay, this is not to be confused with constant multiples. So back up here, if you have a constant times an x, then we get that constant out as the derivative. But if you have a constant by itself, its derivative is 0. Okay, so those two can often be confused for each other. Part B, we have a power function, x to the 5th. So we're going to bring down the 5 and subtract 1. 5 minus 1 is 4. And so we get 5x to the 4th. For part C, we have a cubic root of x squared. Cube roots and radicals in general, they might look more intimidating, but they are just power functions. Remember, like a square root is the same thing as a 1/2 power. The cube root is the same thing as a 1/3 power. So this is actually the same thing as x to the 2/3. So if we want to find the derivative, we're going to bring down that number, and we're going to subtract 1 from the power. 2/3 minus 1 is negative 1/3. So in order to make this a positive power, we're going to move it down using rules of exponents. So 2 over 3x to the positive 1/3. And then the 1/3 power, again, is the same thing as the cube root. So we can go ahead and change this. This is 2 over 3 times the cube root of x. And that would be our derivative. Okay, so not quite as obvious looking as, 5x to the 4th. But it behaves the same way, and that's the important takeaway here. Just like with part D, 1 over x to the 4th, this is a power function, but you can't just bring down the 4 here because it's in the denominator of this fraction. So because it's a fraction, it doesn't follow this format. It's not 1 over x to the n. It would have to just be x to the n. And we can do that. simply by using the same negative power trick. So I can move this up and just make it x to the negative 4. And then the derivative, we bring down the negative 4 and subtract 1. Be very careful with the negatives here. Negative 4 minus 1 is negative 5. So we get negative 4 over x to the 5th. Okay, so again, when it's in the bottom of a fraction, you have to manipulate it first. Put it in the proper form of just x to a real number, like that. And then you can use the power rule. And part E down here, we have a polynomial. So in order to evaluate the polynomial, we can go term by term because we have all this addition and subtraction. So we're going to have the derivative of 5x cubed plus the derivative of 4x squared plus the derivative of 9x minus the derivative of 7. So we bring down the 3. So we've got 5 times 3x squared plus 4 times 2x to the first, so just 2x, plus 9 times the derivative of x is just 1, minus the derivative of the constant is nothing. So we have 15x squared plus 8x plus 9. And that would be the derivative of this polynomial. Now, in the next example down here, we have another polynomial, and we want to find the value of x for which f of x equals 0. So that's kind of like an algebra problem. That's one that we're used to solving algebraically. But we also want to find the value of x for which f prime is equal to 0. So let's look at part A. So we need to find where x squared minus 4x plus 3 equals 0. And we can most simply do this by factoring. So we're going to get x minus 1 and x minus 3. And so that gives us the two cases. X is 1 and x is 3. So those are the two values where the function is equal to 0, right? We would also call those its x-intercepts or its roots. But for the derivative, we need to take the derivative of the function first. So x squared, that's going to be 2x, minus derivative of 4x is just 4, and the derivative of 3 is nothing. Right. So we're going to set this equal to 0. So we get 2x equals 4. And we get x equals 2. So this is the value where the derivative is equal to 0. Now, I want to go ahead and take a look at what this looks like. Excuse me. I got the curve right here. I've got the points where the function is 0. And now I have the point down here where the derivative equals 0. Remember, the derivative is the slope of the tangent. It is the instantaneous rate of change. Okay, so if we draw a tangent line at that point, this is what that looks like. So you can see the x value of 2. You can see our horizontal tangent going through right there, and it's completely flat, has a slope of 0, right? Because that's what the derivative gives us, the slope of that line. And you can see that this is like a parabola, right? So this is the vertex, and then we have, of course, the x-intercepts back up here. So these are new pieces of information that we can understand by taking derivatives. So that takes us to the end of section 2.1. Let's go ahead and move on to section 2.2 with types of functions that get a little more complicated. We've talked about what happens when you multiply constants by x's, right, by functions. We've talked about what happens when you add and subtract functions together. Now we're going to look at what happens when you multiply functions together. So, unfortunately, it doesn't work out quite as smoothly as the addition and subtraction does. Because with addition and subtraction, you just do the pieces separately and just add them or subtract them together. The product doesn't quite work that way. So the product rule says if f of x and g of x are differentiable functions, the derivative of f times g is f prime of x times g of x plus f of x times g prime of x. So you end up taking the derivative of f times g plus the derivative of g times f. In words, the way that we kind of try to roll this off the tongue as best we can, if you consider the first function f, that's the first, and the second is g, the product rule says we take the derivative of the first times derivative of the second plus derivative of the second times the first. So this is the product rule. Again, it's not quite as nice as just doing it all separately, but this is what we need to adhere to when we have a product of functions. So let's take a look at some examples. So first one here, we have 5x squared plus 4 times x cubed plus 11. We are going to take the derivative of the first times the second plus the derivative of the second times the first. So we take this first derivative, that's going to be 10x, and then nothing times x cubed plus 11. This one we get 3x squared plus nothing times 5x squared plus 4. And so we get 10x to the fourth plus 110x plus 15x to the fourth plus 12x squared. And a little bit of combination, 25x to the fourth plus 12x squared plus 110x. And that gives us our derivative. Now, with ones like this, it's like, okay, well, couldn't we just like FOIL these out and then just do it individually? Yeah, you could. But the point is that the more complicated these terms get, the more helpful this formula becomes. Because if this was 5x squared plus 4 to the 107th power times x cubed plus 11 to the 1000th power, there's no way we're going to multiply all of these out and try to do this one by one. We're just going to take it piece by piece and then handle it using something like the product rule. So similarly, we have g of t down here. So we'll get g prime of t by taking derivative with respect to t of the first times the second plus derivative with respect to t of the second times the first. So we get 2t minus 0 times t squared plus 1 plus 2t plus 0 times t squared minus 4. We get 2t cubed plus 2t plus 2t cubed minus 8t. So we get 4t cubed minus 6t. Okay, or some equivalent version of that. You could factor out an extra 2t if you wanted to kind of break it apart a little bit, but we certainly don't have to do that. Now, one thing to take note of that, again, distinguishes this product rule from things like the sum and difference formulas we talked about in the previous section. The derivative of a product is not equal to the product of the individual derivatives. Okay, so in the previous section, we saw if you add or subtract the functions and then take the derivative, it's exactly the same as taking the derivatives and then adding or subtracting the functions. Not the case with the product rule. Okay, the derivative of the product is not equal to just f prime times g prime. Okay, there is more process to it than just that. Now, continuing on in a similar fashion, we have the quotient rule. What happens when you're dividing functions by each other and you want to take their derivative? Quotient rule is a little bit tougher to remember. So let's get it written down here. If you have the derivative with respect to x of f over g, this is going to be g of x times f prime of x minus f of x times g prime of x all over g of x squared. So we have g times f prime minus f times g prime all over g squared. That doesn't exactly roll off the tongue. A lot of times we do have kind of a mnemonic that we like to use. If you consider the numerator, like the top function, to be the quote-unquote high function, because it's high above the other, and the denominator is considered to be the low function, the way that we would read this is we would take low d high, so low times derivative of the high, minus high d low. So that's the top function minus the derivative of the bottom one, over low squared. So we have low d high minus high d low over low squared. If that mnemonic doesn't help you remember it, don't worry about it. It's okay. But it is important to remember the quotient rule and this specific order. Because with the product rule, you get f prime times g plus g prime times f. If you mix it up, the addition means that it doesn't really matter what order it comes in, as long as you have them paired properly. The quotient rule, however, because it has subtraction in the middle, if you get them mixed up, you will get exactly the opposite of the answer that you are looking for. So we particularly need to be careful when working with the quotient rule to make sure that we have the order correct, so we don't accidentally go exactly opposite of what we want. So let's try this out. Find f prime of 2 for this function f of x. All right, so we're going to do f prime of x. So we have, right, our low function and our high function. So we're going to have low d high minus high d low all over low squared. So as you can see, these quotient rule problems can take up a lot of space on the page. So just be patient with them. Make sure you leave yourself enough room to work on these. So if we take the derivatives now, so we have x squared minus 1 times, that's 3x squared plus 2 minus that function times that derivative, that's just 2x, all over x squared minus 1 quantity squared. I would not multiply out the denominator. It's not going to help you. If anything, we would hope that maybe it would cancel with something. That usually doesn't happen, but it does us no good to expand it out. So I would just leave it like this with the square on it. Don't try to expand it. It's just going to make it more complicated. It's not going to make it simpler. Now from here, we could go through and try to simplify this as much as possible, but luckily for us, we're looking for f prime of 2, so we know no matter how much we simplify it, we don't need the final version of the formula. We really just need to plug in 2, and we can do that at any time. So let's do it now. So we're going to plug in 2, so we get 2 squared minus 1. 3 times 2 squared plus 2 minus 2 cubed plus 2 times 2 minus 1 times 2 times 2 all over 2 squared minus 1 squared. So let's see, that's going to be 4 minus 1 is 3 times 14 minus 8 plus 4 is 12 minus 1 is 13 times 4 all over 3 squared. That gives us 42 minus wait a second. No, that's right. 42. 452. Okay. Sorry, I just had a typo in my notes. I'm going to have to fix that. So that's minus 52. Right? 8 plus 4. Oh, no, because I wrote that number wrong. That's why. This is 8 That's 12 minus 1 is 11. There we go. Nope, my notes didn't have a typo. My brain had a typo. Over 9. So we get negative 2 over 9 is the value of that derivative. So now when we're talking about what this example shows us, we're looking at this function at the value x equals 2. This is the slope at that point. So I want to show you guys on the graph. So here's what this graph looks like. Okay, so it's got multiple pieces, but we want when x is 2. So there's our point right there. And we draw the tangent line. And the slope of this line that I have in orange right here, the slope of this line is negative 2 over 9. Okay, so that's what the derivative is giving us right there. It's giving us the slope of that line, which is the, again, instantaneous rate of change of this function at that point specifically. Right. And just a final note at the end, just like with the product rule, the quotient rule does not have any kind of fun shortcuts or, simple solutions. The derivative of the quotient is not equal to the quotient of the individual derivatives. So you can't just split it up across the quotient. It doesn't work that way. Only addition and subtraction is where we can do that. But that brings us to the end of section 2.2. Let's go ahead and move over to section 2.3. In this section, we are looking at the concept of higher order derivatives. So the derivative f prime of a function f is itself a function, right? We know that if you take the derivative of a function, you get f prime, but f prime is still a function itself too. What that means is we can take the derivative of this new function. So we can take the derivative of the derivative, which would be called the second derivative, which is denoted f double prime of x. And this is also a function. You can take its derivative and then its derivative, etc., etc., etc. So you can keep taking derivatives to your heart's content. So f prime, f double prime, f triple prime. Notice that once we get to the fourth derivative and higher, we don't use the prime notation anymore because it gets really cumbersome. If I want to take the 10th derivative of something, I don't want to have to sit and go 2, 3, 4, 5, 6, 7, 8, 9, 10 of x, something like that. This takes up a ton of space on the page. It takes up my time having to write it. We don't want to do that. So once you pass like the fourth derivative and then higher, we use this parentheses notation, okay, so that you know this isn't a fourth power. This isn't f to the fourth. It is the fourth derivative of f, and then the fifth derivative, sixth, etc. Okay. If we alternatively use the Leibniz notation, the dy dx, we pick up a square on the d and the x. Okay, so the reason that we do that, if you take the derivative with respect to x of dy dx, so this is kind of a shorthand notation here, but we have two d's right here. So that's d squared, dx, dx. There's two of those. And then if you take the derivative again, you get d cubed y over dx cubed, d to the fourth y over dx to the fourth, etc., all the way down. So the Leibniz notation is nice. It doesn't change. It doesn't change form, I should say, as we take higher derivatives. Like the prime notation does. But the nice thing about taking higher derivatives is there's nothing different about it to taking first derivatives. It's not that you're taking something differently, it's just you're doing more of it. So for this example, f of x, find f prime, f double prime, f triple prime, and f fourth derivative. So For f prime, we're going to do the power rule on each of those, and then we'll handle those as well. So bring down the 5, that's 15x to the 4th. Bring down the 4, that becomes an 8x to the 3rd. Bring down the 2, that's 2x. 10 just tags along for the ride. Derivative of x is 1, so that's just minus 10. And then the plus 4 becomes nothing because the derivative constant is 0. F double prime of x, we take the derivative of the derivative now. So we bring down this 4. So 15 times 4 is 60, x to the 3rd. Minus, bring down the 3, that's 24, x squared. Plus 2, right, because the derivative of x is 1, so 2 times 1. And then minus 0. The third derivative is the derivative of this one. So we bring down the 3. That's going to be 180 x squared minus 48 x plus nothing. And the fourth derivative, we bring down the 2. That's 360x minus 48 times 1. So you can see with a polynomial like this, the more derivatives we take, the simpler the function gets. And all we would have to do is go 2 more before we hit 0. But not all functions are made easier with differentiation. You can also have a reciprocal function like this one. So we know that y is 1 over x. In order to take the derivative, we need to put this in the proper form. So that's going to be x to the negative 1. Okay, so we write this as a power function so that we can differentiate. So y prime, we bring down the negative 1 and subtract 1. So that's negative x to the negative 2. So negative 1 over x squared. Y double prime, we do the same thing here. So we bring down the negative 2. So that becomes positive 2 because it cancels. And subtract 1. That's negative 3. So we get positive 2 over x cubed. Y triple prime, we bring down the negative 3. So that's negative 6. Subtract 1. So we get negative 6 over x to the 4th. And then we can evaluate each of these at the value x equals 2. So that's negative 1/4. That is 2/8, which is also 1/4. This is negative 6 over 16. So negative 3/8 if we simplify. Now, when it comes to working with not only first derivatives, but second derivatives as well, working with these higher derivatives, we want to be able to understand and recognize what these derivatives tell us about a function and about its graph. So when we talk about the first derivative gives us slope, right? Slope tells us, like slope of a line tells us whether the graph is going up like this or going down like this, for example. The more technical term that we would use is it tells us whether the function is increasing or decreasing. So increasing or decreasing. As we move from left to right, is the function going up or going down? Okay, increasing, decreasing. If f prime of x is greater than 0, so our derivative is positive, then f is increasing on that interval. If, on the flip side, the derivative is negative, then f is decreasing on the interval. Okay, so again, increasing and decreasing basically just tells us, is the graph going up or going down? So that does give us valuable information, but now when we talk about the second derivative, the second derivative tells us about the function's concavity. Now, when we talk about concavity, what I mean by that is the concavity of the graph of the function tells us how the curve bends. So concavity is this idea, it's the derivative of the derivative. So it's not just, is it going up or going down? It's how is it going up? How is it going down? Is it going up faster and faster and faster? Is it going up, but it's kind of going up more slowly as we go? Is it going down and it starts to go down faster and faster and faster? Or is it going down more slowly, right? It's kind of leveling off here as we go. These are questions that we want to answer with concavity. So if f double prime is greater than 0, so if the second derivative is positive, we say that f is concave up on the interval, which means that it is upward bending. And if f double prime, that second derivative, is less than 0, then the graph is concave down on the interval. And that, again, is downward bending. Oftentimes, you'll see these abbreviated as CU and CD. So concave up, concave down. Again, where concave up tells us that the graph is bending upward, concave down tells us the graph is bending downward. So I want us to visualize this. So I've got two graphs here, just general graphs. The graph on the left is the graph that is concave up. So you can see the second derivative is positive everywhere. But notice that on the left side of this graph, the first derivative is negative because the function is decreasing there, right? So we're decreasing on this side, we're going down, even though the graph is concave up. Because even though the graph is going down, it has an upward bend to it, right? The slopes are really, really negative, but they start getting less negative. They start leveling off and getting closer to 0 as we go here. And then on the flip side, still concave up, but this time we're increasing on this side, right? The graph, the slopes are getting higher and higher and higher and higher, right? Steeper and steeper. So this is a concave up graph. We can remember this is what it looks like because it looks like the letter U, like up. On the flip side, a graph that is concave down has a second derivative that is negative, but it could be increasing or decreasing. So again, concavity does not tell us whether the graph is going up or going down. It tells us if it is bending up or bending down. So for the concave down graph, if it's increasing, the values are headed up, but they're starting to be less and less, they're increasing less and less as we go forward, right? They're very, very steep, very, very large, and they're getting smaller and smaller and smaller, right? Still increasing, but bending downward. And then on the flip side, slopes that are negative, it's going down and it's bending down. So it's starting to get down faster and faster and faster as we go. Okay, so this is the idea with increasing and decreasing found using the first derivative, and concave up and concave down found using the second derivative. We will be talking more about these concepts and how we can use them in the upcoming chapters. So, hang on to these ideas. We will be revisiting them later on. Let's take a look at an example, a little bit of application in here. Suppose the function c of t represents the amount of money in thousands of dollars a city spends on social programs t months after the beginning of the year. Interpret the information provided by c prime of 9 equals 2.5 and c double prime of 9 is less than 0. Okay. First up, the 9. That is a t value. T represents time, represents months. Okay, so we're talking about 9 months. So we can say after 9 months, which if you're thinking in terms of what month that is, that would be in September. September is the 9th month. We have the derivative, or the rate of change, of the amount of money spent. Okay, so money that the city spends. The rate of change of spending is 2.5, and that is in thousands of dollars. So we can say after 9 months, the amount of money being spent on the programs is increasing by, that's 2.5 thousand, so $2,500 per month. And then this one, we have c double prime is less than 0. So this tells us, right, concave down. So even though we are increasing, the values are leveling off. They're getting flatter, right? They're steadying. So we can say that after 9 months, the amount of money being spent on the programs is increasing by $2,500 per month, but it is increasing at a decreasing rate. Okay, so we're still adding money into the programs, but the amount of money that's getting added is getting lower. Okay, so the amount of money that they spent is increasing by $2,500, but maybe the previous month the value increased by $3,000, and maybe next month it'll only increase by $2,000. The amount that it's getting increased by is less and less and less. So we can say, so future increases will not be as much as 2,500. Okay. So they're not saying that they're taking funding away. They're not losing money. It's just that the amount that it's increasing by is getting smaller as time goes on, okay, as the months pass. All right, so that is the end of section 2.3. So now let's head into section 2.4. And we've got a couple more rules to look at. In particular, one of the more important rules in derivatives and differentiation, and that is the chain rule. The chain rule helps us take derivatives when you have functions inside of other functions. This is really powerful when you have more complicated functions. So we say if y is a differentiable function of u and u is a differentiable function of x, then dy dx equals dy du times du dx. So the derivative of y with respect to u, derivative of u with respect to x. Now, the way that we interpret this, if u is inside of y and x is inside of u, we think of this in terms of inner and outer functions. So the alternative notation that we will use is going to be this one. So the derivative of f of g of x, that's going to be f prime of g of x times g prime of x. So if you have a function inside of another function, okay, so if we take the derivative of a function with another function within it, we must take the derivative of the outside function first, leaving the inside alone, then multiply this by the derivative of the inside function. So you take the derivative of the outside function first times the derivative of the inside function. Okay, so let's take a look at how this would work. So we ease into this first using this u notation. So we have y equals 2x minus 9 squared plus 3 times 2x minus 9. If we identify u as 2x minus 9, that gives us a general formula now for y in terms of u. So that's u squared plus 3u. So if we wanted to find the derivative, this would be dy du times du dx. Derivative of y with respect to u, that's 2u plus 3. Derivative of u with respect to x is just 2. So we get 4u plus 6. U is 2x minus 9, so we get 4 times 2x minus 9 plus 6. So that's 8x minus 30. That would be how we would do it using the u notation. But I want to offer the alternative here, like if we wanted to use this notation, because this is the one we're going to be working with most frequently. What we would do is we would take y prime equals derivative of 2x minus 9 squared times derivative of 2x minus 9 plus, there's not really any need for the chain rule on this one, but so for this one, we would bring down the 2, and we would be left with a 1, right, because of the power rule. So we perform the power rule on this. We leave the inside alone, times the derivative of the inside, which is just 2, plus 3 times 2. So we get, again, 8x minus 30. So the chain rule definitely takes practice. We're going to do some more examples in just a minute, but it definitely takes work and some getting used to because we are applying derivative formulas still, but we're applying them to multiple functions. So again, like we would bring down the 2 for the power rule, but we would leave the inside intact and then multiply by its derivative over here. Part C of this just said evaluate the derivative at 5. We can absolutely do that. So y prime of 5. That's 40 minus 30 is 10. Now, the chain rule can be extended to any derivative formula that we have and any one that we need. It's not limited to one specific type of function. And technically, it's getting used all the time, even when we don't know that we're using it. Because if you were just going to take like the derivative of x squared, something like that, you would take the derivative of the outer portion. So you'd bring down the 2 times the derivative of the inner portion. But the inner portion is x, so its derivative is 1. So you would just get, 2x times 1, but that's just 2x. So technically speaking, the chain rule can apply everywhere. So if you're ever in doubt or you're not sure, better to just use it, be safe, rather than be sorry and then you missed out on it. But one place that it comes up so frequently, and we just used it right there, is in employing the power rule. So we have what is called the general power rule, also known as the extended power rule, depending on like the text that you're using. So this version says that if y is a differentiable function of u and u is a function of x, y equals u to the n, where n is a real number, then the derivative is the power rule. So you bring down the n, you subtract 1 from the power, but then you multiply by the derivative of the inside function there. So this is the derivative of the exponential portion, so the normal power rule, times the derivative of the base. That is the extended portion. Okay, that is the chain rule portion. And again, this rule is just a specific case of the chain rule. There's nothing different about it. It's just that it comes up so frequently, they like to mention it separately. But the chain rule and this general power rule give us a lot of power in computation to solve problems like this first one, like part A. If we want to find the derivative of this without the chain rule, we would have to FOIL this out, or not even FOIL because there's 3 terms. Distribute this out 6 times, expand it all into one crazy long polynomial, and then go term by term and take the derivative of all of them. We don't have to do that here anymore. So what we can do instead, we have the inner function here. The outer function is the power. So we'll take the derivative of the outside. So we bring down the 6. Subtract 1, so that's 5. Times the derivative of the inside function. So it's derivative of the outside times derivative of the inside. So we have 6 times 4x cubed plus 5x plus 2 to the 5th times 12x squared plus 5. And that would be the derivative. And if you did this, by distributing and expanding and going term by term, you could then theoretically factor it back and you would get the same answer, okay, or an equivalent version of that answer. But we were able to just do it here in one step instead of doing all of that extra work to try to solve it out. Here we have a rational function. So I'm going to go ahead and rewrite this one in our typical power function form. So the 4 is there. We have 6 minus 2x to the negative 2. Okay, I did that by moving it up. F prime of x, we bring down the negative 2. And we subtract 1 times the derivative of the inside function. So let's see here. That's negative 8 over 6 minus 2x cubed times this derivative is just negative 2. So that's positive 16 over 6 minus 2x cubed. Okay, again, the alternative without the chain rule is to expand this out and then use like the quotient rule on it. So this allows us to avoid having to use some of those more complicated rules like the quotient rule. And lastly, down here, we have a radical function, which again can be rewritten as a power function. So this is going to be the 3/5 power. So if we take dy dx, we bring down the 3/5, subtract 1 from the power, that's negative 2/5, times the derivative of the inside function, derivative of the 7x minus 8. So we're going to have 3 over 5 times 7x minus 8 to the 2/5 times derivative here is 7. We'll combine those two. So that'll be 21 over 5. And you could leave it as a fractional power. I'll put it back as a radical because that's what the problem gave us. So that would be the 5th root of 7x minus 8 squared. So that would be our final version of that, kind of simplified down a bit. All right, but that brings us to the end of section 2.4. That is the end of our work in chapter 2. So we've introduced a lot of derivative concepts, derivative formulas. We've done some practice with a bunch of different functions. When we come back in the future chapters, we'll be looking at more derivative formulas, more applications of derivatives, and we're going to be seeing kind of a lot of the different stuff we can do with them in the next couple of chapters before we get to around the middle of our course. So I will talk with you all in the next one, and I hope you all have a great day.